Welcome to section 12.1. We're dealing with the introduction to limits, and we've talked about limits in end behavior before. Where does something approach? But we've never looked at in the midst of a function, and so we're going to do that today. What I want you to do is start with the intro, and we're looking at a line 1/2 x plus 1. And so what we want to start doing is graph that first. And so as I graph this, I know I have a y-intercept of 1, and I go up 1 and over 2. For my slope. So this is linear, and as I look at this, here's what I find. I get this line. Okay, now, as I look at this line, the question is, what happens when we get close to x equals 4? And so when we describe a behavior, we want to look right around that point that we're trying to find. And so what I want to first do is just by what we call direct substitution, plugging that value back in. And if I plug in 4 into my function, what I end up getting then is a value of 3. Now, what I want to see is as I look around this graph, do I actually seem to get 3? And so graphically, as we look at 4, if I go to 1, 2, 3, 4, I can kind of see that's right here. And yes, it does look like as I come from each direction, as I look in each direction, what y value am I approaching? I can kind of see from the graph that I'm approaching the y value of 3. Now, not all of the time are we going to have you use a graph. We are going to sometimes say, let's look at a table. And so what I did is I put this equation in my y equals menu. And then I started hitting the value button in my calculate menu. And so when I plugged in 3.9, I got a value of 2.95. And when I plugged in 3.95, I got 2.975. And 3.99, I got 2.995. Okay, so I kind of plugged in values. 4.01 is 3.005, and 3.025, and then finally 3.05. And our question is, what value do we expect to get here? And as I look at the table, it seems like I'm going to get 3. And so because we've looked at it in two ways, both graphically and numerically, what I'm going to say is the limit of my function f of x as x goes to 4. So as I approach 4 on my function, what I expect the number that I'm going to reach is 3. And we're going to write our answers in limit notation, so just kind of be aware of this as we go through. So let's try another one. Let's take a look at example B. Now, as I look at example B, you'll notice now we have a fraction. We want to know behavior again as we get close to 4. So what I'm going to do first is plug in the value of 4. And so what I have is if I plug in 4, it doesn't even matter what the top is, because if I plug in 4 into the bottom, I get a fraction that's undefined because I can't have 0 in my denominator. So let's go graphically. I'm going to plug this in my y equals menu. Don't forget parentheses on top and parentheses on bottom. And I'm going to take this and graph it. And here's what I end up finding. At 0, you get 2. At 1, you get 3. 2, you get 4. 3, you get 5. When I hit 4, there's nothing. So I'm going to leave that blank. It says error. At 5, I get 7, 8, 9. And you'll notice it's linear on either side. Now, to finish my graph, what I'm going to do is actually look at my table. And so when I plug this in and I hit, value, what I'm going to look at is if I plug in a 3.9, I get 5.9 out. And if I get 3.95, I get 5.95 and 5.99. So what that says is even though I don't have a value directly at 4, because at 4 gets me that error in my calculator, there are values directly around that. And the way we just show that on a graph is we put an open circle at that value, and then we connect our line on either side. And what that says is at 4, there's what we call a hole. And so it may not be evaluated at 4, but there's values everywhere around it. So 4.01 is 6.01, 6.05, and 6.1. And so as I look at this, where do I expect the value to be at 4? As I look at it, again, it seems to be 6. And so I'm looking at this and I'm going, yeah, but I have an error. And so, okay, if I'm looking at it, again, the question isn't if the value exists, it's more where am I approaching? And so as I look from the left and the right, what I'm getting to is this value of 6. So I say the limit of my function as x approaches 4, I think it's going to be 6. Okay, because again, graphically it looks like it's approaching the value of 6, and numerically it's approaching the value of 6. It may not actually touch 6, but that's where it's approaching. And so what we want to say basically is the limit, and what the biggest part of this, the limit exists even though the function is undefined. So a limit can exist even if a function value doesn't exist at that point. Now, let's go back to my original problem because I want to talk about why there's this hole in my function. Well, if I look at this here, what I'm going to do is factor this. If I factor the numerator, I get x minus 4 and x plus 2 all over x minus 4. And what you'll notice is these can cancel out. This factor that cancels out, this is what creates the hole. It doesn't just drop out of the situation. It just creates this hole right here for what's missing. And you'll notice the rest is a line, y equals x plus 2. And so what it does is it leaves the original factor, but it creates the hole where you get an undefined fraction with your denominator. So just keep in mind, again, if you can factor it, that's things you should look at. If it's not factorable, then just go right into your calculator. So let's talk about the definition. Basically, as we look at this, the limit as it approaches a number L when x goes to c. So what we're saying is the limit of a function as x gets closer and closer and closer to some constant value is L. And L is just a number, and it's just a unique number that it approaches. And it has to be a real number and a quantity that you can actually say. So it's not infinity, it's an actual number. So let's keep going. Let's look at some areas that we have issues with, and I'm going to draw pictures for you also. Now, what I want you to do is put this graph in your calculator, and then I want to draw a graph, and I want to talk about kind of what happens. As I look at my graph, I have 1 up here, I have -1 down here, and that's kind of important. And so as I look at this, your graph goes like this. Now, let's talk about what happens at the y-axis. I have to have open circles in both places because I can't have an x value of 0 or I get an undefined fraction. So I've got an open circle and an open circle, and they kind of go in opposite directions at values of 1. Now, if I look at my limit, okay, my limit, although it's not there, my limit is approaching 0. As I go to 0 from the right-hand side, I have a value of 1. As I approach it from the left-hand side, I'm at -1. Because these two numbers are not the same, the limit, we say, does not exist. And you can write out does not exist, but I'm just going to shorthand it here. And again, we want to kind of write something out. Because it approaches two different y values, the limit does not exist. And again, you're going to want these descriptions as you go back. You're going to want those descriptions as to why it didn't work. So if you're trying to go to a value and you're approaching two different numbers, the limit does not exist. So let's take a look at the second one. We're going to put this in our y equals menu, and we're going to look at a graph. Okay, if I look at my graph looks something like this. Now, I am again going to approach 0. As I come from the right, I'm approaching infinity. As I come from the left, I'm approaching infinity. I cannot have that because this has to be an actual real number. And so it does not, this is another area, it does not exist. Okay, so the limit has to approach a number cannot go to infinity. Okay, or negative infinity for that matter. In this case, though, we're just looking at infinity. Okay, last type. If you put the sign, and I'm sorry about the look of this, put it in parentheses 1 over x into your calculator. We're again going to look as x approaches 0. Okay, so as we do this, let's take a look at what the graph, and your graph, please make sure you zoom trig so that you're in sine. But here's what happens. It gets really big, and then it starts going little and little and little and oscillates. And this is called an oscillating function. And an oscillating function basically means it's going to jump up and down, up and down, up and down, and up and down all the time. And it's going to get, as it gets closer to 0, the jumping becomes, it jumps quicker. And so it's never going to approach a single number because it keeps jumping. So oscillating, because it jumps, is the way I'm going to say, never reaches a specific number. Okay, so again, oscillating functions, we call this one an unbounded limit because again, it goes up to infinity or it'll go down to negative infinity. And this one we look at where it approaches 2 different values. Okay, so those are the 3 major areas that are problems, and you will want to make sure that you go through and you look at those and look at the graph beforehand, but kind of keep a look at the equations and what they look like, because those are the big indicators of where problems occur. Okay, so I'm going to slide to the next page. All right, we are talking about different limits and properties of limits, and so those are things that you're going to want to look at. These basic limits are on page 857, and it's the idea that you're using what we call direct substitution. Direct substitution. Okay, and so here as we look at it, here's what it says. The first one, the limit as x goes to some value of c, and c can be whatever it is. If you're looking at just the limit of one number, you're going to end up with the number because it's a y value, so you're going to end with a y value. If you take the limit as x approaches a number of an x, think of the y equals x line. When you plug in the number c, you're going to get out a value of c. The third one, the limit as x approaches c of x to some power. As you look at this, equals, I'm going to take this and I'm going to plug c in for x, so I'm going to get c to the nth. If I take the limit as x approaches c of the nth root of x, again, when I plug a c in for x, I get the nth root of c. And I just want to add something on here as well. All trig functions can be used with direct substitution as we're going through also. So kind of keep that in mind. Now I'm going to show you general ideas, and what it says, I'm going to look at what types of things I can do. So I'm going to start with this idea for properties of using a scalar, and a scalar just means you're multiplying a number. So if I take the limit as x approaches a value of c, and I'm going to take some scalar b, so some number, and I'm going to multiply it by my function. Well, what it said above is if I take the limit of the function, I get a value of L. Well, if I multiply it by a scalar b, I can take the limit itself, which is L, and multiply it by my scalar. If I look at this idea of a sum or a difference, then I can take the limit as x goes to c, and I can add f of x, or you could subtract it. So I'm going to put plus or minus g of x. Now, since I'm going to the same value c for both of them, the limit of f is L, and the limit of g is k, so all I have to do is add or subtract k, depending on what my function is asking me to do. I also have this idea of a product. So if I'm going to multiply them, where I take the limit, again, as x goes to c, and I'm going to multiply f of x times g of x, what I can do is multiply their limit values. So L times K. Let's do the next one, quotient rule. Again, these are all in your book, but I just want to kind of run through them with you. If I take F and I divide by G or vice versa, all I can do is divide their limits as long as K doesn't equal 0. That's the biggest thing, because if the limit of G is 0, then I can't divide them because I get an undefined limit. Last one is the power rule. And again, as I take the limit as x goes to a value of c, and I take a function and raise it to an exponent, it's just like this idea over here where I take that. I know that the limit of f is L, and so I can take L to that exponent as well. And so these are some of the properties we're going to be using as we go through. So let's give a couple. And again, this idea is really direct substitution. We're going to plug the value in. And so we're going to use the power rule from above, and we're going to look at it and say, okay, if I plug a 2 in, then I take 2 cubed, and 2 cubed is 8, so the limit is 8. And again, most of this we're just using direct substitution if we can. So the next thing, let's try the next one. If I plug a 4 in, I have 7 times 4 then, which is 28. All right, if I directly plug this in, I have the sine of pi all divided by pi. Well, the sine of pi is 0, so 0 divided by pi is just 0. Okay, and it's, again, this all is idea of direct substitution. Let's plug d in. If I plug a 25 in for x, the square root of 25 is 5. And most of these you would find if you look at a graph. But we're just trying to give you, instead of having to look at a graph, let's make this even easier. All right, let's put in a pi. If I put in pi times the cosine of pi, well, the cosine at pi, or 180, the cosine value is -1. So I have pi times -1, which is negative pi. Oh boy, you can't forget your trigonometry stuff, can ya? All right, take a look. Let's directly substitute. 2 plus 3 squared. That gives us 5 squared, and 5 squared is 25. Just a couple more. Plug in a 2. All right, 2 cubed plus 5 times 2 minus 6. Well, I've got 8 plus 10 minus 6, and 18 minus 6 is 12. All right, let's plug the next one in. I have 2 squared minus 5 over 2 minus 3. So 4 minus 5 is -1. 2 minus 3 is -1. So -1 divided by -1 is just 1. And last but not least, let's take a look at this. If I plug in a 3, 3 squared minus 5 over 3 minus 3, we should see an issue. Okay. We cannot, in this case, use direct substitution, because what happened was I got an undefined fraction. So cannot use direct substitution. What you can do is look at the graph. So let me slide this up a little bit so I can show you the graph. As you look at this graph, again, if you put this in your calculator, since direct substitution doesn't work, we have to look at another method to be able to find the limit. Well, if I look at this, here's what happens. 1, 2, 3. My graph looks something like this. And if you notice, here's 3. What's happening? As I go to get closer to 3, my graph is going down to -infinity. This is one of those areas where we have an issue, because I have something that's unbounded. I mean, as I look at this, it's approaching -infinity. And because it's unbounded, this limit does not exist. And so direct substitution is great for 90% of the time. It's these issues where you have something that you can't substitute in that you have a problem, because if I can't directly substitute, I have to look somewhere else. Now, you could have used a table, the numeric method, or you could have used a graph. It didn't matter, but you had to find another method for it. So that's the introduction to limits. Again, what we're going to do is start looking at problems. We're going to start talking about homework things in class. But if you get a chance to start again, start the homework so you can ask some better questions when you come in. So that's it for section 12.1.